Hello everyone, today I wanted to discuss forces, which is basically imagined as a push or pull on an object. Now, Newton's law of motion, specifically his second law of motion, is what we'll be discussing. And it basically gives us a formula of how to find force based on what is called mass and then, of course, acceleration. So, again, on forces, and Newton says the following, that force is equal to mass times acceleration, where m of course is mass and a is acceleration. So this is mass, acceleration, and of course we have some standard units here. Now the unit for acceleration, the standard unit we have of course is meters per square meters per second squared is what I meant to say. Mass, the standard unit, believe it or not, is in kilograms. Okay, and force, the standard unit of force is a Newton, denoted by capital N. So 1 Newton is defined. So I'm going to use this 3-bar version of equality, which basically means, by definition, is 1 kilogram multiplied by 1 meter per second squared. So it's just kind of the culmination of these two units together. Okay, good. So that's kind of like the first thing we'll be seeing. In fact, I'll just do a little quick example of this. So find the force acted on an object with mass, let's say 32 kilograms. Let's just say 35 kilograms. If the resulting acceleration is, let's say 40 meters per, no, that's too much. Let's do 4. 4 meters per second squared. Now, of course, this is a pretty basic problem because we already know everything that's given to us. We have the mass m, we have the acceleration a, and the units are correct. So right away, just multiplying these, let's see, we're going to get that the force is, of course, mass times acceleration, which is 35 multiplied by 4, which will give us 140. And the unit's going to be kilogram times meter per second squared, which we now know is newtons, or capital N. Good. And as we move on in this discussion, we'll kind of find a little more will be unveiled to us as far as different units we're kind of used to that are somewhat equivalent to newtons. In fact, one we'll see right now is pounds. So when you see pounds, you may think of that's a weight. Weight is actually a force. It's a force due to gravity on an object. So we'll take a look at that and a little more right now. Right, so very much like we saw previously, we have our F equals ma formula, but it's a little different, of course, because this is F net. So in reality, the sum of all of the forces is equal to the mass times the acceleration. And notice that this is all vectored quantities here. So very often we're actually going to break down into the components of these vectors. So we're going to very often consider either horizontal or vertical forces, and with that, horizontal and vertical acceleration so that they match, of course. Okay. Now I mentioned also I'd give a conversion between pounds and newtons, and here it is. 1 Newton is 0.225 pounds, which is pretty close to a quarter of a pound, and for that reason there's this pretty popular physics joke where they say that a quarter pounder, like the burger, is a Newton burger. It's not very funny of a joke, but I just kind of thought I'd throw that out there. Also here, 1 pound, much like 1 Newton, is kilograms times meters per second squared. 1 pound is what is called a slug times feet per second squared. So this is kind of like the mass equivalent of what kilograms is in a metric, but now the mass unit, standard unit, I guess you can say, in imperial. Also here we have weight. I'm calling this W, which is also referred to as F sub G, which is just the force due to gravity. And I mentioned that that's what that is. So these are the two notations of that. And of course, that's just mass times gravity, because that makes sense because gravity is an acceleration, as it turns out. And here I'm writing gravity, I'm writing G for gravity as in gravity on Earth. But we'll actually see, after this example, we may do a few examples involving finding your weight on a different planet with a different gravity. So we'll be taking a look at different gravities in different planets. Gravity here is 9.81 meters per second squared. On a different planet, it may be more or less, depending on how far the planet is away from the sun, basically. And here I want to do this example. It's a little bit of a kind of overwhelming example, but let's take a look in any event. So here I say a boat weighing 800 pounds, including the items and people on board, has an engine that produces a net horizontal force of 2,000 pounds after accounting resistant forces. And we're asked to find these three items: the acceleration of the boat, the time it will take starting from rest to achieve 50 miles per hour, and then find all resistant forces if the engine is shut off after reaching 50 miles per hour in part B, and it drifts to a stop after a distance of 200 feet. And I'm drawing a little picture here. We have this boat, and there's two forces. Notice I'm writing these arrows to represent the directions of the forces. We have the force supplied from the engine, and then we have the resistant forces, which could be wind or the resistance of the ocean, just whatever resistance we face when traveling. And notice here it's a negative force going in the opposite direction. So with that being said, when we find the sum of all of these forces, since this is negative, really the sum of the forces is the engine force minus the resistance force, and that together makes the total net horizontal forces, which is 2,000 pounds. The weight of this boat, that I'm calling W, including the people and everything else on the boat, is 800 pounds, and that's all really given from the initial statement. And now from here, I'm going to erase everything. I'm going to probably move this picture up along with what we're being asked, and then we're going to continue to actually solve A, B, and C. And it's not really going to be too bad, as we'll see shortly, so let's take a look at that right now. So here I've slightly worded some things, and I moved the picture up here, of course. But this is basically what we had previously. And the kind of funny thing about this problem is we're going to actually stick to imperial units, which I think makes sense because we're given pounds, miles per hour, feet. We're not given meters or kilometers or newtons or kilograms even. So for that reason, we'll just stick to imperial. So of course, we need to find mass. That's the biggest thing here because we want to use F equals ma. In fact, we want to use F net is equal to mass times acceleration. So we need the mass of the boat to find the acceleration of the boat because we already have the net force of the boat. Net force is 2,000 pounds, yeah? Now we need to find the mass. The good news is we know the weight is 800 pounds. So let me write here that our weight is equal to 800 pounds, but we know weight from our previous discussion is mass times gravity. And we know gravity in feet per second squared, which I believe was 32.19. I actually forget exactly what it was, but let's just say it's 32.2. So the mass we don't know. This is 32.2, let's say, feet per second squared. And the weight is 800 pounds. So we already said that pounds is equal to slugs times feet per second squared. So the mass here will be in slugs. So all we need to do now is use our calculator to divide 800 by 32.2, and then we'll get our mass in slugs. So I'm just going to do that real quickly here. And I got 24.8 about. And let me just kind of include here, since I've included the units here, might as well include this to be in pounds. And then dividing both sides by this number, 32.2. I guess feet per second squared if you want to include the units in the calculation, which I very often don't do. But that's okay. Just to kind of see that happening here. Since pounds is slugs times feet per second squared, canceling these out will actually just leave us with the unit slugs. And like I said, the answer of this division was 24.8. So our mass is equal to 24.8 slugs. Perfect. Now we can plug that in here to find acceleration. So that's 24.8 times the acceleration. Now dividing by 24.8 here. So remember again, you kind of see the units playing the role a little bit. This 2,000 is in pounds, but we already saw when you divide pounds by feet per second squared, you get slugs. Similarly, if you divide a pound quantity by a slugs quantity, you get the other unit feet per second squared. So namely, the acceleration after doing this division will be definitely in feet per second squared, and that'll be our answer. So now what we need to do is plug this into our calculator, see what we get. I'm just going to do that here real quick, and I get about 80.6 feet per second squared, and I'll write my answer. Oh, I'll box this, of course, but I'll write it over there, boxed as well. So it's 80.6 feet per second squared. Awesome. So now we'll move on to the next problem, part B. So I'm going to erase a bit of information here. I think we still need mass, maybe. Maybe we'll be okay. So I'm going to erase some things and then we'll see how we can tackle B. All right, so now for part B, we're asked to find the time to reach 50 miles per hour starting from rest. So that's assuming that we're going at the same acceleration from part A. So probably didn't write down the detail, but that's what we're assuming. And basically part B is a kinematic equation problem, and this is one-dimensional. So we could recall the kinematic equations if you like, but just know we need a kinematic equation that has time, final velocity of, maybe I should just write it down like this. Sorry about that. So we need time, we don't know time. We have the final velocity is 50 miles per hour, that's fine. And rest. What does rest mean to you, do you think? If we start from rest is actually a key word. Rest basically means that the initial velocity is 0 miles per hour, or whatever the unit is, but in this case, miles per hour. So rest, the word rest implies that this is 0 miles per hour. So let me just say that's from the word rest. So keep that in mind, because that honestly plays a role quite a bit in physics, in word problems especially. And we know the acceleration is 80.6, and that's in feet per second squared. Oh. The reason why I made that noise, of course, is because we do not have matching units here. This is miles per hour, and that's feet per second squared. So we need to convert this somehow to feet per second. Well, we've seen this before, actually. Oh, by the way, we technically need to convert 0 miles per hour to 0 feet per second as well. But that's a lot easier. It's still going to be 0. So let me just erase the keyword rest and say that this is 0 feet per second. That I think should be fairly obvious. Because when you're converting, you're just multiplying by a factor, and 0 multiplied by anything is still 0. And we actually have seen before that miles per hour, using a conversion table, you can convert miles to feet by multiplying by 5 to 80, and that'll get rid of the miles. And to get rid of hours, you would need to multiply by 1 over however many seconds are in an hour, which is 3600. So that converts miles per hour into feet per second. You just have to multiply basically by this number here. And notice I'm dropping a 0 because that's just dividing by 10. So I'm going to multiply 50 by this real quick, and I'm just going to do it right now, I guess. And let's see what we get here. So I got 50 times 528 divided by 360, and I got 73.3. So this is 73.3 feet per second. Now that we've taken care of the units, so everything's in the same unit, we can definitely find time, and that'll of course be in seconds, because our time unit now is in seconds. So let me erase this conversion here, and let's see if we can figure out which kinematic equation we should use. Notice the variable missing here is delta x. The only kinematic equation that does not have delta x is the first one, which is v equals v naught plus a times t. Now, something I actually haven't done is you can actually solve for the variable first and then plug in. That, of course, is just a thing from algebra. So I'll do that here just to show you. So I'm going to subtract v naught to the other side to get this. And then, of course, dividing by the acceleration gives us a right away. So a is equal to v minus v naught divided by a. The really nice thing about doing this is because you can kind of see in this particular case, v minus v naught is just 73.3 minus 0, which is just 73.3. And that's in feet per second. We're dividing by acceleration, which is in feet per second squared. So notice that's just the feet cancels, and then second over second squared, or I guess 1 over second divided by 1 over second squared. Kind of like a double reciprocal thing. You end up getting seconds. And that's something I've kind of avoided talking about, is the units, so long as they're all in the same unit as far as distance units and time units go, then everything will just kind of come together nicely, and then our time unit will be in the correct time unit. Our time variable will be in the correct time unit. Well, in any event, let's see what we get here using our calculator. And I got 0.909. I'll round that up to 0.91. So that's in 0.91 seconds it takes for that to happen. So that's from here, just to kind of complete things a little bit. And that's our answer for part B. So let me write that in red and box that. So it's 0.91 seconds. And now we can try part C finally, where we find a force yet again. But just to kind of brainstorm a little bit, I'm going to find a resistant force only. So notice resistant force was the negative force, engine force was a positive one, and the net force was engine force minus resistant force. But in this problem, we're shutting off the engine, so now there is no engine force, it will be 0 now. So our net force will just be this. So we kind of have to redo A a little bit. So I'm going to erase this and we'll start that process right now. Right, so like I previously mentioned, we'll be using net force is equal to engine force minus resistant force. But since we are shutting off our engine, and that means this goes to 0, so the output is no longer 2,000 pounds. In fact, the net force now will just be the negative resistant force. So it's going to be a negative value because it's going in the opposite direction that the boat is headed towards. So that's fine. But there's all this other stuff that's given here. Let's see how we're going to apply this. So after reaching 50 miles per hour, so as soon as we enter problem C, our starting velocity is 50 miles per hour. So let's kind of keep that in mind. So our initial velocity now is 50 miles per hour. Okay. We know F net is negative resistance force, so let's see how that will come into play. I think what's kind of going on here, and you can kind of tell maybe a little bit, is we know the mass, and we also know force is mass times acceleration. So with everything else that's mentioned here, we can actually try to find acceleration, multiply that by the mass, and then we'll get the force, the net force in that case. So our initial velocity is 50 miles per hour. It comes to a stop after 200 feet, so its distance, delta x, is going to be 200 feet. We actually converted 50 miles per hour into feet per second earlier, and that was 73.3 feet per second. That's the initial velocity. Do we have final velocity? We do. Why do we? Well, because it says it stops after that. So that means we have no velocity if we've stopped. Kind of like how starting from rest means you have an initial velocity of 0. When you stop, similarly, you actually have a final velocity of 0. And that's in feet per second. Perfect. And now we're going to try to use these to find acceleration. That'll, of course, be in feet per second squared since all of our units line up nicely. We'll figure out what that is using some kinematic equation. Then we'll multiply that to our mass in slugs to get our negative resistance. So hopefully it is a negative value that we get. But then that means that the resistant force we can just write as a positive value because that'll just be the magnitude of that. Or we could write it as negative. I guess it's kind of to be seen. But let's see. Let's see if we can figure this out together. Which kinematic equation will we use? Not 1, because 1 didn't involve delta x. In fact, notice the one missing here is t, and the only kinematic equation without the time variable is the fourth kinematic equation, which is v squared equals, there we go, v naught squared plus 2a delta x. Perfect. And we want to find a, so let's do what we did before. Let's solve for that ahead of time. So let's subtract this to the other side to get this. Perfect. And then this is, notice it's equal to 2a delta x. So if we just divide both sides by 2 delta x, then you'll get a by itself. So let me show that cancellation in red. 2's cancel, delta x's cancel. So we indeed get a by itself. So that means a is equal to v squared minus v naught squared over 2 delta x. Now v squared is 0 squared, so that's just 0, so don't even write it. Minus v naught squared, 73.3 squared is 5372.9. this rounds to 5372.9. It's negative because of the minus in front of V naught squared, over 2 times delta x. Delta x is 200 times 2 will be 400. So notice we indeed get a negative value. That's good. And the units are going to line up, and it is indeed going to be in feet per second squared. So let's divide our number by 400. Let me just kind of make sure I have the estimation correct. Yeah, I got about 13.4. So this is about 13.4, and that's in feet per second squared. So I'll just write it here for completion. Perfect. Oh, that wasn't our answer though, was it? Because we're not trying to find that, it's asking to find resistant forces. So I probably shouldn't actually box this, but this is a pretty good achievement because now that we have acceleration, we can multiply that to our mass. Our mass hasn't changed because we haven't removed anyone from the boat or anything like that. We've only shut off the engine. And it doesn't change the weight of the boat as it turns out. Removing people from the boat or items from the boat would change its mass. But anyways, now that we have that, let me erase this and we'll finish off the problem. Okay, perfect. So we know F net is equal to mass times the acceleration. We know the mass is 2.48 slugs. We know the acceleration is 13.4 feet per second squared. So multiplying those units will of course give us a new unit in pounds. And multiplying these numbers together, so that's 13.4 multiplied by 24.8 gives me 332.3. And notice F net is actually just the negative resistance force. So that means the resistance force is this negative value. So it wasn't negative already, which actually, you know what? I think I skipped something here. So when I did the calculation, I forgot to carry over the negative. Remember there was a negative in front of that number that was, it was like 5,379 or something like that. So this actually should have been negative. So that was a typo I had made. Which is good because now this is negative. That's what I was kind of hoping for. Since this says it's negative, then that means we should get a negative here because this resistance force without the negative represents the resistance force as a positive magnitude. So magnitude is always positive for vectors, which I know sounds confusing because sometimes we think of vectors as being positive or negative depending on direction, but that is the vector with the direction in mind. Remember, directions are vectors are direction and magnitude. So we need the number and the sign if it's a one-dimensional vector. The sign would give you the direction. The number itself, the absolute value of the number that is, would give you the magnitude. So that's a little technical. But anyways, here we have 332.3 pounds. That's the resistance force. So I got a little confused when writing the acceleration. It should have been negative, not positive. So that was my mistake from the previous screen before I erased stuff. But you can go back and check. That should definitely have carried over the negative. Anyways, so now that we're done with this is kind of like the biggest part of the video. The next thing I want to talk about is how you can calculate your weight on a different planet. And then I'll talk a little bit about friction, and that'll be the end of the video. Right, so as previously mentioned, I want to discuss how we can find our weight on a different planet. Now, the detail of this comes in what is called Newton's universal law of gravity. Basically, this says that the force of gravity between two objects in space in the universe is given by this equation here, where G is known as the universal gravitation constant, which is this number, 6.67 times 10 to the negative 11, with this very strange unit. Now, this unit isn't actually that strange when you come to think of that M1 and M2 are masses in kilograms, and R is the distance between the centers of masses of those objects in meters. So when you square that, you get meters squared. When you multiply kilograms to kilograms, you get kilograms squared. So in multiplying this number to this quantity here, units should cancel so that we get a resulting force in newtons like we expect. Now here I've drawn an image where we have these two objects. You can think of them as particles or planets or whatever the case may be in space. And their distance from the center of mass of the objects is given by R. And notice here we have this attraction between the objects where the force of one is Fg and the force of the other one is negative G because, of course, it's in the opposite facing direction. Now, consider that you are on a planet. So here I'm drawing this large circle representing the planet, and then you representing this smaller circle on the planet. And notice if you actually take the distance from the center of the planet to the center of you, of yourself, you're super small compared to the planet, so the distance between you is approximately the radius of the planet itself. So that's something to keep in mind. In fact, in particular, if the planet has mass capital M and you have mass little m, then your weight basically is the force between the planet and yourself. So it's kind of like the force that the planet is using to pull you down so you're stuck on the planet. Kind of imagine this attraction, only we're always sticking to the planet that we're on. So that I think should make sense. Now notice since your weight is given by mass times gravity, the gravity of the planet, you can actually divide both sides by your mass, and you get now a way to calculate gravity of that particular planet. It's just the gravitational constant, g, multiplied by the mass of the planet divided by the radius of the planet squared. Of course, the further you are away from the planet within the planet's atmosphere may make the gravity change. So imagine you have like a balloon, for instance, that's floating and it's very, very high up in the atmosphere of the Earth. Then this radius, this distance that is actually larger than the radius of the Earth by a little bit. And for that reason, the gravity that applies to those balloons up there may be a little different the further you are into the atmosphere away from the Earth. But that's, again, a technicality. So great. So I'm just kind of keeping this in mind. And in fact, this is what you can use to calculate gravity of other planets. Now, we're not going to be doing that, luckily. We're just going to be given certain gravities on planets and given our weight on Earth, we can calculate our weight on those planets. So now let's take a look. So for this example, if we weigh 180 pounds on Earth, we want to find our weight in pounds, I should say, on these other planets. Now, the thing we should probably do first, since these are in meters per second squared, which kind of comes to mind, is convert this to newtons. And notice that if we weigh 180 pounds, let me kind of create a conversion table here. And we know that 0.225 pounds is equal to 1 newton. All we have to do is divide by 0.225. Now, when you divide 180 by 0.225, you actually get 800 even. So let me just write in red here that this is equal to 800 newtons. And also notice that that is our weight. So our weight is 800, and also weight is equal to mass times gravity. And since this is our weight on Earth, then we can subscript these with capital E for Earth. And we know this is 800 newtons. We don't know our mass, but we do know gravity is 9.81 meters per second squared. So that means our mass in kilograms would just be this divided by 9.81, which should give you about 81.5. So let me just write that over here, kind of erase this. But if you divide by 9.81, you'll get that, 81.5 kilograms. So that, let me just say that's equal to m, your mass. Good. So now that we have our mass in kilograms, we can multiply that by gravity to get our weight on those certain planets. So for, now the moon isn't a planet, but it's a body in space, so it's fine. So if we want to find our weight on the moon, this is just our mass multiplied by the gravity of the moon. Easy enough. Now notice what this kind of tells us is that our mass is universal in the sense that our mass does not change no matter what planet we're on, but our weight does because that's influenced by the gravity of that planet or body. So if we multiply 81.5 by 1.62, which is the gravity of the moon, we will get about 132. And that's going to be in newtons. Now, if you multiply this by 0.225 to get back into pounds, this will be about 29.7 pounds. In fact, notice, in the grand scheme of things, all we really have done, well, we multiplied by, we divided by 0.225 to get from 180 to 800, so to convert from pounds to newtons. Then we divided by the gravity of the Earth to get our mass. And then we multiply by the gravity of the moon to get back into our weight in newtons. And then we multiply by 0.225 to get back into pounds. So in fact, notice we're just multiplying and dividing. And we multiplied by 0.225 here, and we divided at the very beginning of 0.225. So in reality, that step kind of cancels out. So really all you really have to do is multiply by your new gravity and divide by your old gravity. So if you actually took 180 divided by 9.81 and multiply by 1.62, you'll get this exactly anyways. So I'm going to skip a little bit of steps here, and I'm going to keep that in mind. So to find our weight on Saturn, all I'm going to do is get my initial weight on Earth, which is 180, and I'm going to multiply by the new gravity, the gravity of the planet that we're on currently, and divide by the gravity of the planet where this weight was. So divide by 9.81. And if you divide by 9.81 and multiply by 10.44 and multiply that by 180, you will get about 191.6 pounds. Perfect. So these will be your weights on those planets. Now, given the gravities, this makes a lot of sense because the gravity here is less than 9.81, so we'll be weighing less on the moon. But on Saturn, for whatever reason, probably because the mass is way larger than that of the Earth, even though it's pretty far away from the Earth, its gravity is larger than 9.81, so we'll actually weigh more on Saturn than we would on the Earth. Perfect. So that's all I want to say as far as this goes, and now we'll take a look at something else. All right, so what I want to talk about right now is what is called normal forces. And the best way of understanding normal force is basically it's just the force that opposes gravity so that something has no vertical movement. So we have three different cases here. We have these two cases where you have an object that's on a level surface, and the last case where it is not on a level surface, it's on a slope surface. Here, the difference between these two is that we'll have an applied force, so it's going to be actually moving horizontally. I kind of imagine a box, and you're moving a box with a rope at an angle, then the box will kind of move like this, but we're not lifting it vertically at all. So I'm going to denote these normal forces by n. It's a vector n. We want to find the magnitude of this vector n. Now notice that the arrows pointing down represent the vector of force due to gravity, which we know to be the weight, which is just mg. And in fact, since we know that this is a downward acceleration, we'll call this negative mg. In other words, this is the vector considering the direction and magnitude, as we've kind of seen before. Good. Now, in this case, again, since all of the forces sum to the net force and there's no vertical movement here, then what this tells us is that the net force is 0, so that the sum of these forces, n plus negative mg, is 0, so this implies that n is equal to mg in this particular case where we're on a level surface with no applied force. Okay? Here, if there is an applied force, let's call it F applied, and it's at a certain angle, we can actually break this up into its components. So specifically that's F app y, and then here, this would be F app x. And let's call this angle theta. And what you'll notice is that, of course, if we have our understanding that the y component of this force is just the, because remember this is the vector technically, so that the magnitude of the y component is just the magnitude of the force multiplied by sine of the angle. So what we end up getting here is something kind of similar to what we get here. Basically what we get is that the sum of these two vertical forces minus this force end up giving you a 0 net force because there is no vertical motion, only horizontal. So from the applied force, we're only taking the vertical component, adding it to our normal force, subtracting the gravity force, and we end up getting, well, 0 as a result because, again, there's no vertical movement at all. So what we end up getting here is that n plus the y component magnitude, which again is just the force, the application force magnitude multiplied by sine of the angle, and then minus mg, and that's equal to 0 because again this is what is called an equilibrium basically. There's no vertical movement. So now solving for n here, we can just subtract these to the other side. We actually end up getting that n is equal to mg minus the force of the application, the applied force, times sine of theta. In this case, good. Now in this one, it's a little kind of harder to explain, but I'll try to do so in a less detailed manner. I mean, I'll still be a little detailed about it. But let's imagine that the incline of this slope is the angle theta. Okay, so if we actually create a vector going down like this, as it turns out, this angle, believe it or not, the angle here, is also theta. Now, why is that? If we take a look at this triangle here, this is taken to be 90 degrees, so this would have to be 90 minus theta. And the reason there is because all angles in a triangle add to 180, so that would have to be 90 minus theta in order to add to theta and 90, that right angle, to amount to 180 degrees total. And with that being said, then this angle here, using this large triangle, right triangle, that would also have to be theta. So the more you think about it, the more it actually will make sense, and you'll kind of see that that will indeed be theta. So again, that really doesn't matter too much though. What I want to get out of this is that if this is mg, and this is like our hypotenuse, so to speak, of the right triangle. So again, negative mg is this opposite side right here. I guess it'd be adjacent to theta. So with that being said, you can actually find the hypotenuse by considering cosine of theta. Cosine of theta would be the adjacent side divided by the hypotenuse side. So the hypotenuse side would be this multiplied by cosine of theta times mg. So this right here would be negative mg times cosine of theta. Perfect. Now, with that said, we're actually in a good state. So if you look at this line right here, the sum of these forces in this direction will be 0 because there's no net force here. There's equilibrium in this direction, this weird angle direction. So that being said, if we add these, this plus this negative value will give us 0. So that means this normal force must be having magnitude equal to this without the negative, kind of like what we did here, just add it to the other side. So what we end up getting here is that the normal force is equal to m times g times cosine of the angle. And the last thing I'm going to talk about is friction. So there are two types of friction. There's kinetic friction and static friction. Kinetic friction is friction when you have two objects that are moving, or basically it's friction during motion. So imagine you're dragging an object along a surface. Depending on the surfaces, you'll have a different coefficient of friction between those two surfaces. So for example, if you're dragging a wooden crate over concrete, there is a specific coefficient of kinetic friction between those surfaces. Static friction, though, is a little different. So the way static friction works is that you have two objects that are not moving, so they're static, meaning that they're not moving. So the maximum static friction force would be the force you would need to overtake those frictions so that you have some type of sliding going on. I know that kind of sounds weird, but let's imagine that we have, and you can actually perform this on your own, this experiment on your own. You take your favorite object that you feel has some type of friction to it, not like a ball or marble, something that's not like that. So imagine let's say a Rubik's Cube. So if you put a Rubik's Cube on, let's say, the face of a hardcover book, and you lift it up to change the angle, at some point, at some angle, that Rubik's Cube will start to slide. Right before it slides, that basically will give you the point of the maximum static friction force. And you can actually, there's actually a way to compute the coefficient of static friction based on that scenario setup I was showing you, that I was just explaining just now. But you can look into that a little more if you'd like. I'm not really going to be discussing this in too much detail here. I'm just kind of slightly introducing these things. And so we now have an understanding of what these frictions are. So the coefficient of frictions, again, depends on the surfaces specifically that we're dealing with. And that's basically it. But now I want to discuss the force due to these frictions. So for whatever reason, capital F is not used here, unfortunately. We use lowercase f for whatever reason. So lowercase f sub k and f sub s are the kinetic and static, respectively, forces. The only difference is that for static force, you'd actually need the max static force in order to match the definition here for the kinetic friction force. So the kinetic friction force is just the coefficient mu sub k, which, by the way, is a coefficient, meaning that there's no unit attached to it, multiplied by the normal force. So that's why I've introduced normal here, normal forces. Similarly, the max static force is the coefficient of static friction multiplied by the normal force. Now, the actual static friction force is found basically just using kind of knowledge of vectors, like kind of what we did here. And then you'll see if the max static force given the coefficient of static friction is less than or bigger than that. So the actual static force Fs must be less than or equal to the max static force. Otherwise, there's motion and the object actually falls. So again, that's by the way, this is bigger than or equal to 0. So that's a little detailed for our discussion. I'm not really going to get into too much more detail involving that. There's one more thing I do want to discuss though, which is tension. Now this video is getting a little long, so I'm going to do something a little different. I'm actually going to complete the problem and then I'll kind of walk us through the steps. So let's take a look at that right now. All right, so tension basically I'm describing here is just forces needed to balance equilibrium. So of course, when you think of tension, it's really on a rope or string. And what's happening is tension is the force that's counteracting the opposing forces that are creating that tension. So normally what you think of is something like this example here, where we have an object being held where there are 3 ropes, so there's tension on each of the ropes. And in this particular case, it's an equilibrium. I say or if there's a net force. So if there's an actual non-zero net force, there's something similar you can do. I'm not going to talk about those types of problems here. But let me just say if there was, let's say, a kind of lifting, let's say like lifting a guy or something like that, or even an elevator, you can actually translate it to an equilibrium problem by just adding a weight to the object being held in equilibrium. Something to think about, but anyways, that's an idea. Now here we're given these angles of these ropes, and I'm translating it into this kind of more standard view where we have this XY plane. Good. And I notice for T1 and T2, we can break it up into their components. There's T1Y, T1X, T2Y, and T2X. Notice T1X is going to be negative. Great. Also notice we have these angles here are actually equivalent to these angles up here, and that's due to parallel lines. If you create a parallel line here, this angle will be equal to this angle because of what are called alternate interior angles, which you don't really need to know the details of, but it's a result from geometry. Similarly, these angles are equal as well. Good. And notice T3 is the tension on this object, and it's purely vertical. The weight of the object is given to be 120 newtons, which is good. And we actually know that it's downward, so we're going to associate that with a negative weight. And to actually find T1x, T1y, T2y, and T2x, we can just multiply the magnitudes of T1 and T2 by cosine and sine of the angles to find the x and y values respectively. Just like this. Also, since it's in equilibrium, because there's no motion, there's no swaying or up and down movement of this object at all, then the horizontal sum of forces will be 0, and the net vertical force, the sum of all of the vertical forces, will also be 0. So notice I'm adding T2x to negative T1x, And remember, when I say T2x and T1x, we're multiplying T1 and T2, respectively, by cosine of their associated angles. Similarly for the verticals, but notice here we have this negative 120 on this side as well, because we had this additional vertical component here. So you kind of, if you just look at the arrows, there are 3 vertical arrows associated with tensions. So these 2 and this one going down. So notice we have 2 pluses and 1 negative. And for the horizontal arrows, we have this T2x and this negative T1x. So positive and negative, positive, negative. Great. Now using our calculator, we can actually approximate each of these cosine and sine values, and we get this following system of equations with T1 and T2. Solving that system, which I didn't show the work here, but it's not too bad. In fact, notice if you just subtract this to the other side, or I guess add it to the other side really, and then divide by 0.53, you can get T2 in terms of T1, substitute that into this, and then solve for I guess it would be T1. And then from there you can substitute back to find T2. But I did all the work here for us. I'm just kind of walking you through the steps. And we end up getting this. The tension on the first rope here at the angle of 32 degrees is about 63.6 newtons. And the second tension here for the rope with the angle of 58 degrees has a tension force of 101.8 newtons. And the third tension was already given, that's just the weight of the object itself, which is 120 newtons. Awesome. So that's all I wanted to say as far as forces go. I know it was kind of a long video, but this is basically all you need to know as far as forces go. Now, we're not quite done though, because the next thing we'll talk about will actually incorporate forces, and we'll kind of see a little more of that come into play. Kind of like how we saw stuff from motion with kinematic equations come into play a little bit here, we'll be seeing forces come back to bite us a little bit when we talk about the next topic, which of course is energy. So I'll see you in the video for that. Thanks for watching. Hope you enjoyed. See you then.